I'm Cody Lynch, and I worked on water harvesting for my capstone project with my advisor, Jeremy Qualls. So, water harvesting is basically finding new sources of water, new ways to produce water in our world. And so what this graphic shows is the darker regions of the graph show where water is really readily available, where clean water is available to almost everyone. And so as you can see, that's most of North America. But in the lighter regions, it shows places where less than 50% of people have access to clean and drinkable water. And this poses a lot of problems, obviously. Almost 4,000 children die every day due to the poor water hygiene in these other countries. Almost 2 million people die every year from all these waterborne diseases that they are forced to drink. 1 billion people are left without drinking water, and 2.6 don't have the proper sanitation for the water that they're forced to drink. So that leads us to trying to find new sources, and that's what I was working on. One of the first ways that people tried to water harvest was through a process called dew harvesting. So I think all of us are familiar with going out. If we go out early in the morning, you look on your lawn or on the ground, and there's dew that's collected overnight. And so what people first try to do is harness that dew by they would leave out a tarp overnight, and then along with collecting on the grass and everything else, it would also collect on the tarp, and then they could collect water from the tarp. So that just shows like the lengths people are willing to go to try and get clean water. So the goal of my project was to collect clean drinking water, and I wanted to do it in a way that was completely solar powered, so just by this ambient energy, so just energy from the sun. And I wanted this to be an inexpensive design that could be deployed anywhere in the world, because as you can see, we don't really need help with water collection here. It's other regions that need it more than we do. So as Jeremy was saying, there's a long history of water harvesting at Sonoma State, going back to 2012. The first project started with dew harvesting, and that student was able to collect 20 milliliters of water in just one day. So 20 milliliters isn't very much. I think it's about a sip of water. But then the next year, another student worked on an absorption system. And with his condensing and absorption system, he was able to collect 150 milliliters of water, so almost half a cup. So we're getting closer. Then there was work made into solar absorption cooling, which is where you work on cooling down a surface using methanol evaporation. But a problem arose with that was where if the methanol were to leak out of the cooling chamber, you'd contaminate your water, and if methanol gets in your water and people drink it, you could go blind. So that was sort of a dangerous way of cooling. And then 2016 was when I started, and then I worked primarily over the summer on optimizing a desiccant solar still. So it's pretty similar to a dehumidifier where it pulls water from the air, but it's not using electricity or any toxic materials. So my processes for collection were using condensation, which is where the water vapor in the air would collect on cold surfaces and turn into liquid water, and then I would collect that liquid water. The other thing I harnessed was a strong desiccant, and what a desiccant is it's a material that can readily absorb water out of the air. So that was the main way of collecting the water harvesting aspect. And then I wanted both of these processes to be completely powered by solar energy, so just energy from the sun, the heating from the sun would run both of these processes. The desiccant I chose to use in my project was montmorillonite clay. And there was sort of a process I went through to choose this, so I'm going to go over it. First of all, this clay that I chose only costs $15 for 2 kilograms of clay, and everything else for the same amount of desiccant would be over $25. So it was already the more inexpensive option. Then what my graph shows is how well the desiccant collected at certain humidities. And so at lower humidities, there were 3 main candidates. There was calcium oxide, the clay that I chose to use, and then something called a molecular sieve. And all 3 of these could absorb water to a pretty high degree at low humidities. Then when you went to how quickly they could absorb, how fast you could absorb this water from the air using your desiccant, you saw that calcium oxide takes a very long time and it doesn't actually collect as much as the clay or the molecular sieve. Both of those can saturate within 4 hours. So if it was being left out overnight, which is what I did, it could collect very quickly as opposed to needing upwards of 12 hours. So that narrowed it down to 2 different desiccants. And then what the third graph shows is what temperature you need to get that water then out of your desiccant. So when heating your desiccant, how much can you get out? So the clay, the montmorillonite clay that I chose, can expel most of its water at less than 100 degrees Fahrenheit, which is ideal for leaving out in the sun. And the molecular sieve, you had to get most of its water out, had to be over 300 to 400 degrees Fahrenheit, so you'd have to bake it, essentially. So it wouldn't have worked. So that narrowed it down to montmorillonite clay, and that's what we chose to use. So I started this project over the summer of 2016, and over that summer I came up with a few prototypes. My first prototype was able to collect 30 milliliters of water in just one day, and then I tried to improve on that, and then there's my second design, and it shows that I was able to collect 40 milliliters of water. And then the last design I was able to build over the summer was the best one, and it was able to collect 60 milliliters of water in just one day. The important thing I learned from all these designs was the amount of clay actually had a lot to do with the efficiency of the water harvesting. So if you increase the amount of clay, you can also increase the efficiency of the water you get out of the clay. I was only able to do 2 trials, so the data might be a bit skewed, but the general trend is there, and that's when you increase the amount of clay, you can also increase the efficiency that the water is produced. So this was the final design that I came up with over the summer, and it's just a single column design, and this column can hold almost 2 kilograms of this montmorillonite clay and produce that 60 milliliters of water. So I'm going to go into how exactly it's able to do that. It's a pretty simple design. We just have an outer shell, and inside that is this wire mesh with a cone inside of it. And so what you don't see is that where I put the clay was between this wire mesh and this outer shell. So there'd be a very thin layer of clay there. And what I would do is in the evening, when it started getting cool, I would open up my design, I'd take the cone out, and then air would be able to flow into the design, and it would saturate the clay. Then in the morning, I would come out and I would seal the whole design, make everything sealed, and then the heat from the sun would heat this outer shell, and then that outer shell would therefore heat the clay, and the clay would release all of its water. That water would then condense on this cool surface, which would be my cone, and so there'd be liquid water condensed on the cone, and it would just drip down into this collection chamber. And that's sort of how the process worked. So this semester, what I wanted to do was scale up this design, because I found that scaling up the amount of clay also improved the efficiency. So what I did was I changed that 1-column design and I upgraded it to a 7-column design. So I would be expecting to get that 60 milliliters of water from each cylinder, and so that would be about 420 milliliters of water a day or a night. So because I said earlier scaling improves efficiency, I was hoping to get between 400 and 500 milliliters of water a day, which is about half a liter. So the assembly for this larger design took longer than I expected. I had to build a drainage system that would connect all 7 columns to one central drainage tube and would drain it all into one central collection chamber. So this was the drainage system I built. It's made out of just wood and 3D printed parts that I got to use the makerspace for. And I connected all these columns to that one drainage system, and then I put it inside one larger outer shell. I used just a large dark trash bin for my outer shell because it can collect, it's dark enough to have the sun heat it just enough. And then I filled the space between all these columns with the montmorillonite clay. So now the final design looks something like this. So to the naked eye, it may just look like a garbage bin, but in reality, it's got a lot going on inside. So the interior is similar to the other one. It has clay between each of the columns and those wire meshes. And so in the So when this clay is saturated, it would be heated by the sun. This whole design gets hot to that 100 degrees or 90 degrees, and it starts to expel the water I collected over the night. That water then condenses on these cones and then drips down through the drainage system into that one central collection chamber. Then in the evening, when you would come out to open up the design so they could saturate, or sorry, so it could collect water during the night, you could also pump out the water you'd collected that day. And so that's when you'd collect your waters in the evening. Then you open up the design, you can take the cones out, so it's just the clay being left in there, and then air can flow through up through the pump or out through the top, and then through the drainage pipes, and it just resaturates the clay overnight. And so having the 7 columns gave me more surface area so I could collect more water. And during the day, of course, you come out and you just close the top and put the cones back in, and you can begin collecting water again. So moving forward, what I would have wanted to do is test my design more. I didn't get many chances to test it. It just recently started getting warm again, so that was a big factor. I'm still expecting to get between 400 and 500 milliliters of water, so still getting that half a liter. And so what I wanted to figure out was how the cost compares to other, like getting water here or in other countries, how the cost, like, was it worth buying? So what I determined was you could really only use this design during the hottest part of the year, so let's say 3 months out of the year. And then the materials like the clay and the plastic, if you leave it out in the sun and the clay is being saturated and then having the water expelled from it eventually degrades and the plastic will degrade. So we only expected the design to last 2 years. But overall, it should only take about less than $50 to construct. So we're seeing that it's about 41 cents a liter. And if you were to leave this device out during the rainy season, if you were to just use it as a collector, just as a bucket to collect water, it improves the cost efficiency even more. So as you can see, as we've gone through the years, starting with dew collection and then the absorption prototype, and now we have this desiccant prototype, we've been improving. And so hopefully that trend will continue moving forward. We're not the only school working on water harvesting and pretty much the same method. This was a project that was done with combined efforts of UC Berkeley and MIT, and they built a device where their desiccant, instead of using clay or any normal material, they have a metal organic framework. And what that does is it's just a better desiccant. It's powered by the solar panel on top, and it's a much stronger desiccant. You can get 3 liters of water a day using this design. But the downside to this was, well, it required electricity, or at least a solar panel, and the materials are expensive. It's expensive to build, and it can't really be sent anywhere. So this design can be used here in the U.S., but I don't know how well it would do if we sent it to other countries. And so that's what I was trying to do with my design. And go back a second. That 41 cents a liter is actually very similar to what people in other countries pay for their water. I know even a bottle of water, which is 1/3 of a liter, costs $1 here, and this is 41 cents for 3 times that. So it ended up being as cost efficient as I hoped. I'd like to say thanks Steve Anderson for his help constructing my design. I couldn't have done it without you. And then I'd like to thank Mike and Sheila McQuillan for their funding of my summer research. Thank you.
Time for questions. Any questions?
Yes.
How much does the water taste like clay?